Welcome to The Explainer. You know, every single day, millions of us step into an elevator without even thinking about it. But behind that simple act of trust is some absolutely incredible engineering. So today, we're going to pull back the curtain on the two lifelines that make elevators one of the safest ways to travel. And we're basing this on a really deep technical analysis from the experts at Noven Puya Elevator. All right, let's just get right to it. It's a classic fear, right? The elevator cables snapping. But the truth is, a free fall is pretty much physically impossible, and the reason for that comes down to two totally separate but perfectly connected safety systems that act as the elevator's ultimate fail-safes.
You know, the analysis from Noven Puya frames this in a really cool way. Think of it like this. You've got a vital artery that does all the heavy lifting, day in and day out. And then you have this silent last line of defense that only kicks in if something goes haywire. So let's start with that main artery.
Okay, so lifeline number one is the system you might actually catch a glimpse of at the top of a shaft. Those incredibly strong steel wire ropes that hold and move the entire elevator car.
But here's the thing, these are way more than just simple ropes. We're talking about a precisely engineered system that is built to handle just immense tension all the time. And they're not just holding the car you're in, they've got to support a whole lot more.
And this is what's so fascinating. Everything the engineers have to factor in. They're calculating the total force based on the weight of the car itself, that's M-car. Then you've got the maximum number of people inside, the M-load. Plus, there's a huge counterweight that makes the whole thing efficient, MCW. And get this, in a really tall building, they even have to account for the weight of the steel ropes themselves, that's M-rope.
So when you add all that up, how do they make sure it's safe? Well, that brings us to one of the most important ideas in all of engineering, something called the safety factor.
And here is the absolute key. Engineers never, ever design something to be just strong enough. The safety factor is all about asking, okay, what's the absolute worst-case scenario, the maximum load this thing will ever face? And then they make it way stronger than that. It's intentional, massive over-engineering.
So just how massive are we talking? Well, according to international standards, which the Noven Puya analysis points to, the safety factor for a typical traction elevator is somewhere between 10 and 12. That means the ropes aren't just a little stronger than they need to be, we're talking a whole other level of strength.
This chart just makes it so clear. To put a safety factor of 12 into perspective, if the ropes need to be strong enough to hold one elevator car full of people, they are actually engineered to be strong enough to hold 12 of them. And that's not even counting the fact that there isn't just one rope. There's a whole bundle of them working together.
Okay, so the ropes handle the weight. They are ridiculously strong. But what if something goes wrong with the motor and the car starts to speed up? That's where our second lifeline comes in. And this is what really completes the whole safety picture.
Meet the governor. This thing is a completely separate, purely mechanical device. It has one job and one job only: to watch how fast the elevator is going. It's like a silent watchdog, just constantly monitoring the car's speed.
The moment, the very instant that car starts moving just 15% faster than its normal top speed, whether it's going up or down, this incredible device just springs into action. And the best part? No computers, no complex electronics, no power needed. It's all pure, reliable physics.
Okay, let's walk through this because it's awesome. First, the car starts going too fast. As the governor spins faster, simple centrifugal force throws a couple of weights outward. That physical movement is what slams the brakes on the governor's own pulley, locking it in place. Now, here's the genius part. The governor rope is now stopped, but the elevator car is still moving. That motion yanks a lever on the car itself, and that final action drives these huge, powerful brake wedges right into the steel guide rails, grinding the car to a super fast but safe stop.
And when I say yanks, I mean it. That pull is not a suggestion. To make absolutely sure those brakes engage, international standards like the EN 8120 demand that the governor rope has to pull that brake lever with a force of at least 200 newtons. So what does 200 newtons even feel like? Imagine someone suddenly yanking a rope attached to that brake lever with a 44-pound weight. It's not a gentle tug. It is a forceful, unmistakable command that screams, "Stop now." So you see, we have these two amazing lifelines. One is built for just overwhelming brute force strength, and the other is built for lightning-fast speed detection. But they're not just two random parts. They're designed from the very beginning to work together as this one cohesive system you can trust.
And this really gets to the core philosophy that the experts at Novenpuya highlight. It's all about integrated design. You see, you can't just have strong ropes or a good brake. Real safety, true safety, only happens when both systems are engineered to work in perfect harmony.
And that right there, that's the whole picture. You've got the powerful steel ropes, the workhorse, handling all the weight with this insane safety margin. Then you've got the governor, the guardian, always watching the speed, ready to slam on the mechanical brakes in an instant. Together, they create this incredible system of redundant safety. It's just brilliant.
All of this is engineering we never see, but it's the very foundation of the trust we put in a technology we use every single day. It's a silent, brilliant system designed not just to work, but to never, ever fail.